Hello, everyone, and thank you for coming to my talk. Today, I will be explaining to you a bit about Kubernetes, a bit about operating systems, a lot of things in the middle. So hopefully it will be educational, but also entertaining. Before we get into all of that, let me just talk a little bit about myself. Some of you may know me as an open source guy. So I've been in and around open source communities all of my life. As both an individual contributor, but also as a governance of open source. So I used to help big companies do the right thing with open source communities. Now I have a company of my own, so hopefully we're doing the right thing. I have a lot of opinions about that, and you can actually find them on Twitter at our header. But I also just hack on software still, right? You know, there's a pretty big selection of software that I've had a privilege to work on. But today we will be mostly talking about operating systems and software that is related to that. And as I mentioned, you know, I've always been very curious about startups, you know, joined a few of them. But now that I got bitten by an entrepreneurial bug myself, with a few friends of mine, we started this company called ZEDEDA. So in a sense, we will be talking about all of these things out of the list of things that we can potentially talk about. Now, the central question of today is what is an operating system and how can we build the best possible operating system to run Kubernetes and K3s? Now, you may actually think that answering that question should be simple, but it's not, because answering that question would essentially require to answer you a question of what is a computer. And if I were to look back at my own history with computers, I would have to say that I actually went through stages of computing. So my first device that would even resemble anything that could be called a computer was just a desk calculator, right? You would punch in numbers and it will give you answers. The second calculator was very interesting, though. A couple of things about that one is that, first of all, unlike the first one, you would be very hard pressed to find an equal button on it because it used reverse Polish notation. And the reason it did that is because it was actually a programmable calculator. So instead of just punching numbers, you can actually put little programs into it. And those programs would compute on the numbers instead of you doing all of the computations. Of course, then, just like anybody else, I graduated to a personal computer. That was actually a very interesting one. It was a Soviet computer called BK0010-01. And that was one of the first 16-bit PDP-11 compatible personal computers. The only other one that I know of, at least, was developed in the United States called Terak. And if I were to look at the progression between all of these devices, the first one was pretty simple, right? It was just a desk calculator. There was a lot of number punching, you know, writing them down, you know, that sort of thing. That was easy to understand, you know, not too exciting. The exciting bit, which took me a much longer time to actually understand and even learn, right, because I didn't know it at the time, was that was my first experience with what is known as a Turing machine, right? Because Turing machine is this formal definition of what a computation looks like, or a series of computations. But instead of punching in numbers, it has this notion of a tape. But otherwise, it's a very similar concept. Just like my desk calculator has some internal logic to operate on these numbers, you know, a Turing machine has some internal logic to basically process symbols on the tape and give you answers, right? So when I graduated to a programmable calculator, something interesting has happened. Well, first of all, programs for that programmable calculator would look something like that. And of course, I would start by, you know, just doing some really interesting computations, but pretty quickly we figured out that we can actually write games, and that little widget that typically would be used for changing between radian and gradients could be used as a small joystick. So you can even play games on that little guy, right? So pretty soon my notebooks were filled with these types of, you know, really incomprehensible gibberish. There were actually programs for this little computer. Now, coming back to this notion of a Turing machine, I've always thought that this guy was also kind of a Turing machine, but a very peculiar one. And there was something that always bugged me about it. Because unlike the previous guy, this also had an input of a program itself, right? So instead of just putting numbers on the tape, I would actually put a representation of the program on the tape, and then that program would compute on the numbers. And it, again, took me all the way to entering my college years to actually find out that I was basically looking at this difference between just a Turing machine and a universal Turing machine. So a universal Turing machine is basically a program for a Turing machine that then allows it to compute on arbitrary sequences. So it's a program that you can give to a Turing machine, but it's a program that then can take other programs as its input. And that was a very interesting discovery, although again, at the time it didn't feel like a discovery, when I graduated to my third personal computer. So that guy, BK, was very capable. It basically came with its own hardware, which again, as I said, was PDP-11 compatible, the most awesomely designed instruction set you would ever encounter in your life. It also came with something very cool, which was BASIC. And BASIC was this high-level language that allows you to do a lot of things. You can actually write games in BASIC. But I already had my games. I actually had a few games that I really liked on that programmable calculator. So then the question for me became, well, how could I actually run those games on this new personal computer? Now, the answer to that was, of course, obvious, but it wasn't obvious to me at the time, although I actually kind of stumbled into it. Because what I did, I essentially created an emulator for this MK61 programmable calculator that I actually implemented in BASIC. Well, I started implementing it in BASIC, but then I exhausted the resources of the computer, so I actually had to switch to assembly. But the whole idea was that there would be this representation of my MK61 that I can then feed all of my legacy games and actually play games on the personal computer that were originally designed for the desktop, for the programmable calculator. Again, in retrospect, this was a completely nuts idea because I could play much better games, but I like my games. That is the whole gravity of legacy, and we will come to that point a bit later on. So with this story, I think the takeaway from it, aside from a much more simple takeaway that the state of Soviet microelectronics was weird, it was at the same time ahead and behind, its US competition. But the other takeaway is that an operating system can simply be defined as just a program that allows execution of other programs. And by the way, fun fact, those programs used to be called executives. There's actually a great talk by a good friend of mine, Brian Cantrill, which, by the way, if you pause this presentation and you go, watch that talk, I will not be offended in the slightest because he gives a really good history overview of where the operating systems came from, how they intersect with languages and runtimes. I really, really highly recommend it. But again, for the purposes of today's presentation, an operating system is just a program that can run other programs. So what can we do with that? Well, we can actually look at how many of these types of programs do we really need. An interesting observation is that the hardware itself can be a bit of a program because you never quite know whether it's real hardware or not. Because even if you're taking let's say, Intel x86 CPU, the instructions that you're running on that CPU are not actually instructions in a hardware sense. They're instructions in the microcode sense, so they're actually software. So your hardware can actually be software. But at any rate, you typically these days look at triplet of things, which is hardware, operating system, and some kind of a runtime, all in support of a single application. And it just so happens that in the 90s, we got this oversized, feeling that an operating system is the only thing that matters in that triplet. I was very much part of that movement that, felt like all we had to do is find the best possible operating system. This whole battle between Windows and Solaris and Linux, really made me feel like an operating system was this titan that, holds an entire world on its shoulders. But in reality, again, if you look at this triplet, it's actually more like turtles all the way down because we sort of typically deal with 3 turtles, but with virtualization, it could be 4 or 5. It's actually quite a lot of turtles that you can fit into a single computer. Speaking of which, if you take this view of a triplet, you can even go as far as either slicing those individual horizontal sections into specific bits, or you can combine them together. And why this is interesting is because it gives you different architectures for how computers can behave. So on one hand, if you look at my MacBook Pro today, I'm running an x86 MacBook Pro, but pretty soon I'm told by Apple that I will be running an ARM-based MacBook Pro, but all of my x86 applications will still run. Why? Because they will provide an emulation layer that would make it look like my hardware is somehow x86. So that's an emulation that allows you to have multiple hardware views on the same piece of the silicon, right? Then, of course, you can slice running different operating systems on the same piece of silicon. You would use hypervisors to do that. And within the same operating system, you can actually run different processes. So even in that architecture, you would have this really weirdly complicated Russian doll of nesting, but it's basically how my laptop looks today. There's no magic. It's not a contrived example. It's what I do today every single day. Now, we can actually go the other direction and simplify things a great deal. And a great example of that would be a Chromebook, where the runtime, which is obviously the Chrome itself, and the operating system gets combined into essentially a single piece of software that runs on the hardware. But the Chrome OS is this amalgamation of everything that you basically need to run on the hardware to give you an experience of a Chromebook. You can even, by the way, go all the way to combining hardware and the software. That would be an example of something like a Lisp or Forth machine. They're not as prevalent as they used to be. But typically, we still keep hardware and software separate. So at least there are two building blocks. Most of the time, there are three building blocks. So today, in fact, we will be talking how can we look at those building blocks in the most optimal way in 2020? Because obviously, computers have changed a little bit since the times I used my BK back in the 90s. So what would computers look like today? Well, before we talk about computers, let's actually talk about where we can find those computers. And it turns out that the spectrum of computers being deployed is actually vast. So on one hand, you have computers on the very right inside of data centers. These are big machines, doing big things. So think of, public clouds. And all the way to the left, we basically have very specialized computers that can be a smart light bulb or a sensor just sitting out in the field, for 10 years and sending, single samples of whatever environment it tries to sample. And of course, in the middle, we basically have the proverbial edge. By the way, this diagram is taken from a really great white paper that was published by Linux Foundation. I highly recommend you download it because it sort of puts things in perspective as to where we need to think about computation being deployed today. So before we actually talk about the edge, let's talk a little bit about the data centers, right? In the data center today, it's pretty clear what we're running because all of our applications have become containers. I think Kubernetes has one. That is why we're all here. Just like my application for that, tiny programmable calculator was expressed through this, weird set of symbols and packaged essentially in my notebook. Today we do the same, but we package them in Docker containers, right? So everything and anything can be packaged as a Docker container. Then the only question is how can you run that Docker container? And typically in most of the architectures, you run it on a triplet, which is a hardware. Again, not surprising. Then it's some kind of a POSIX operating system. Most of the time it's Linux. But by the way, we actually had examples of Joyent running Docker containers on Solaris, emulating Linux. And obviously Windows is doing the same today. And on top of that, there is some kind of a container orchestration system. And when I really say some kind, I do mean Kubernetes, because again, otherwise we wouldn't be here today. It's not surprising that this architecture is very much in favor among all of the public cloud providers, like Amazon, Google, Microsoft, all pretty much build their data centers in that same way. What's even more interesting is that VMware, that is typically looking at computers that you do not give to your public cloud provider, you still own them and you manage them on-prem, they're essentially building exactly the same architecture with VMware Tanzu. And my favorite example, coming back to Joyent and Solaris and all my friends from Sun Microsystems, there's this company called Oxide that takes that idea all the way to essentially giving you a rack that is built along the same lines. So this architecture has won in a data center. It has won in the public cloud today. So the only question is, what ramifications does it have for the edge? Now, today we will specifically be talking, at least in my presentation, about smart device edge. Again, like I mentioned, there are different kinds of edges. There is on-prem edge, there is access edge, regional edge. Those are more telco specific. And when it comes to telco-specific edges, you can actually apply some of the principles of a data center technology. So you effectively can take a lot of the same software that you run in the data center and just run it on the telco edge. A lot of that is, by the way, standardized through this Linux Foundation project called Acrano, so go check it out. But I will be talking about this smart device edge. I think the jury has concluded the best way to run this type of architecture on smart device edge is a triplet of K3s, not just any implementation of Kubernetes, but K3s, some kind of an operating system or support for the K3s, and obviously hardware is still there. Typically, you deal with x86 and ARM. Actually, when I started the company, I expected to see a lot more ARM hardware. I don't see that much of it, in the field. I do see a lot of hobbyists playing with ARM, but I actually don't see a lot of ARM being deployed by businesses. So hopefully that situation will change. So for the rest of the presentation, let's actually answer a very simple question. So if we have K3s and we have hardware, what is the best possible way of running K3s on that piece of hardware? Is it bare metal? Is it through one of these options on this slide? What is it? Now, of course, I have an answer of my own, but let's actually approach it with an open mind. So let's first of all ask, what does that block in the middle have to do for K3s to be happy? Well, there's actually a lot of things that have to do with the hardware management itself. So there are low-level bits and pieces of the hardware, like trust management, booting, sometimes hypervisors, and I will talk about why. There's a lot of kind of storage management things that can or cannot be moved out of Kubernetes itself, but some of them actually have to be dealt with at the file system level. So for example, if you're trying to orchestrate something like Linux Volume Manager or ZFS, it's rather difficult to do it from within the Kubernetes implementation itself. So there's a lot of low-level plumbing that needs to be done. Now, we have looked at it, and we basically concluded that the best way to do it is to do a specialized operating system. The same way that Docker people have basically did a specialized operating system when they had to run Docker, the engine, on MacBook Pro. Because as you know, MacBook Pro runs macOS. So it's not like you can just take a Docker container and run it there, because obviously macOS kernel lacks some of the primitives that would be required to run a Docker container there. So Docker people had to build this product, which we all use today, called Docker Desktop. And that is effectively a Docker engine plus a specialized operating system that is only there in support of the Docker engine. Now, they called that specialized operating system linuxkit. And we kind of followed in the same footsteps and created a project called Eve, Edge Virtualization Engine, based on linuxkit. So what is Eve? Eve is basically a continuation of a lot of the linuxkit ideas, but into the realm, and I will talk about why we had to do it, into the realm of very sophisticated, or very heterogeneous, I should say, hardware footprint, but also into the realm of not just containers, but also VMs. And again, I will explain why it's important. So the overall architecture of the Eve, it's a specialized operating system that boots. You actually deploy it instead of your typical operating system on a device. It is composed of a hypervisor. That is the first component that boots. And then it runs a control domain, domain 0, full of Eve services that do things like manage your hardware, manage your root of trust, set up your networking, things like that. One of the services in that group is talking to an Eve controller. All the other services are doing something local on the box itself. Now, if you want to run K3s, you would basically instruct Eve through a controller to run a VM, which would be composed of K3s itself and K3OS, just like you would do in a public cloud today. And next to it, you might as well run Windows 10. And again, I will explain why it's so important. So the way to interact with Eve is through a controller, right? Because Eve gets deployed a lot of times behind net boxes and firewalls, you cannot really talk to Eve, even if you wanted to. Eve can talk to the controller and get its state from the controller. Now, the operator actually talks to the controller, and then controller orchestrates a number of Eve devices. Why is it important to have an architecture like that? And I mentioned a couple of times that I will explain it, is because edge requirements are actually much more diverse than a typical set of data center requirements, right? And I'll just focus on 3. I mean, there is more, but I think 3 will really point to why we had to build Eve in the way we did. So first of all is the diversity of the hardware stack, right? On the edge, you basically have a lot of different I/O that needs to be driven. You have GPIO, Modbus, CAN bus, RS-232, different types of hookups. Basically, sky is the limit in terms of how you can talk to an edge device, right? None of it is ever a concern in the data center, because in the data center, your I/O is typically networking, and that's about it. Scale is also interesting because in a data center, you're trying to pack as many containers and VMs into a single server. On the edge, it's exactly the other way around. The amount of VMs and containers on a given edge device is not that great, but you have way more of those devices than you have servers in a data center, unless of course, you're Google or Facebook. But finally, and this is my favorite, subtle difference between the edge and the data center, is that edge doesn't actually have any kind of perimeter. It doesn't have a physical perimeter, and it doesn't have a network perimeter. So it's actually much closer to how you would manage your mobile device, because all of these edge devices are just like your cell phones, right? They're out there, people can touch them, they can try to steal them, disassemble them, try to extract information from them. So that's actually why we keep coming to this analogy that Eve is trying to be Android for the edge, right? Because there is a lot of mobile aspects to what Eve needs to do to secure your edge. Now, a typical Eve deployment, this is, by the way, taken from one of our customers, would look something like this. You would have a hardware, again, like I said, most of the time, predominantly it's Intel because of the legacy. Then on top of that, you would have Eve, and the first thing you would run your legacy VM. Now, that VM would typically be Windows, which explains why Intel is so prevalent. And when people ask me, but why Windows? Can't you just replace everything with containers? The answer is no. And that gets us back to my silly example of a programmable calculator for which I have developed a lot of games, right? It's not that I could not have changed those games into BASIC. It was actually a pretty straightforward exercise. But I already had them, and the experience of having them was very important to me. So a lot of times when you try to deploy a new project into the field, you talk to all of these customers who already have edge deployments. And the first question they ask you, can you run my Windows VM? Because if you're telling them to rewrite all of the application to containers first and only then they can deploy it, the answer will likely be no. But of course, next to that Windows VM, you would run a sort of containers, either through K3s or something like Azure IoT Edge. And that will be this new architecture that will slowly emerge from the account. So Eve inside of it is very similar to how Kubelet would do its thing, right? So Eve has an agent service that would pool, again, because remember, Eve, you cannot talk to Eve. Eve only pools its device twin configs from a controller. So it would pool a device twin config from a controller, parcel it out to the microservices that compose Eve. Those microservices are all eventual consistency, so you are not really sure when they're done, but they always communicate their state back to you. And that state then gets pushed back to the controller and gets reflected in the device twin state. On the development side, Eve is a completely 100% open source project. We've donated it to Linux Foundation, so it's not even, it's a communities project, right? We're still, ZEDEDA is the biggest contributor to it, but the governance belongs to Linux Foundation. All of the development is done through these documents that we publish on the wiki. Think of them as RFPs. Check it out, by the way. It's a good collection of things that you might find interesting about Eve, and it may actually even give you some idea of where you can contribute. We have a pretty good CI/CD system, so if you decided to send us a pull request, that CI/CD system will kick in and help you figure out, what else you might need to polish about your pull request. And finally, Eve actually supports a pretty decent list of hardware, devices on which we run. It's all again on the wiki, so wiki gets updated pretty regularly. There's most of them, like I said, are Intel-based, but one exciting one that I wanted to highlight today is, of course, Raspberry Pi. We added support for it recently, and we actually had to work with upstream Zen community to make sure that Zen really runs well on Raspberry Pi. That actually, quite to my surprise, got covered in a lot of press, like ZDNet, Slashdot, all these other publications, so go check it out. But the fundamental truth about it is that Raspberry Pi 4 specifically is probably the best, easiest way to experience Eve today. In fact, I'm going to demo it right now. Okay, so first step is to actually put something on the SD card to make Raspberry Pi boot with Eve. And one way to do it is to use Eve releases. Eve publishes all of its releases as Docker containers. So if you just run this command like this, right, it will actually tell you, because it's a script, It's a script packaged in a Docker container with a lot of other artifacts that comprise Eve, but it will basically tell you what's capable of. Now, in this particular case, what we're interested in is producing a live image that we can then run on Raspberry Pi. So let's just put it into some kind of a temporary location like that, right? And if you run it like this, pretty soon you will see this file tmp-foo.emg. You can take it, use your favorite burning tool, put it on a blank SD card. That is literally all you need to boot Eve on Raspberry Pi. Very, very simple. Now, while that is actually fun, and you get all of your standard Raspberry Pi tools, like you can actually hook up a monitor and a keyboard and sort of try to see what's going on. It's actually much more interesting to use Eve the way it was intended to be, which is with a controller. Now, Eve actually has two sister projects. One is the open source controller called Atom, and the other project is called Eden. And Eden, think of it as top-level CLI to run both Eve and Atom, in the way that you don't have to be a developer to use it. So in fact, let's use Eden today. And obviously, you need to download it from GitHub. But once you do, you can just type make build. And that will produce a build of Eden. Eden is written in Go, just like everything else we do on Project Eve. And I could have just used the Go compiler, but it's just a little bit nicer to use makefile target. Now, this is actually the last time we will be using makefile, because from now on, we're actually going to use Eden itself to essentially do a lot of things with it, right? So let's first run Eden, and we will see that it's a pretty standard Go CLI. So the first thing to do is to actually build a config. Now, configs are modeled after Kubernetes configuration files. So if you run Eden config, you will see that you can add, delete, edit. It's basically just a nice way to manage your local environment. So if I work with multiple Eves, maybe multiple Raspberry Pis or multiple devices, it's actually very useful. So let's try to add one of the configs, and you will see that you get a choice of a device model. So you can use Raspberry Pi 4, or there's sort of this virtual model. There's actually GCP available as well. So let's just do Eden config add default -- dev model Raspberry Pi 4. So now we have all of our configs set up. And all we have to do is to ask Eden to essentially provision the same image that we did, but also bake a lot of other useful things into that Eden. So in order to do that, you can actually run the following command, Eden setup, and the whole process will get kicked off. It's a little bit longer, process compared to just building Eden, because it downloads a lot of artifacts from Docker Hub, and it puts them together, and it's it goes for a little bit of time. But after it's done, you basically will have the image itself, and I will show you how it would look like. But you will also have a way to actually run Atom. So let's do a jump cut. Okay, so Eden is done putting everything together. So let's take a look at what we have. So there's a dist folder, right? And under the dist folder, you have the default images. And under the default images, you basically have the same image that I produced by just running that Eve release Docker script. It's exactly the same image, but Eden also put a few other useful bits and pieces into it to make your onboarding experience easy. Now, next thing to do, and again, that was a single one-time step, but next thing to do is actually start Eden itself. So you can do Eden start, and that will basically start a few Docker containers. And these are just regular Docker containers, so you can do Docker PS, and you will see that there's a few with the Eden prefix running in your laptop. What they do is they provide essentially useful services to orchestrate all of the Eve's lifecycles. Speaking of which, let's actually boot our Raspberry Pi. But before we do, let's actually make sure that the controller knows about that Raspberry Pi. So while I will be putting the SD card into it, let me also in parallel run this very useful command called Eden Eve onboard, which essentially registers the next Eve that will contact my laptop to be an known Eve to this controller. Again, let me do a jump cut because it takes a little bit of time to put an SD card into Raspberry Pi. Okay, now that our Raspberry Pi is up and running and successfully registered with its controller, let's actually do deployment of two VMs. As I was explaining, for today, we will be trying Windows and K3s, both running on Raspberry Pi. So let's do this one first. So this is a Windows VM. What's interesting about it is that in Project Eve, we actually figured out a way of how to very conveniently package VMs as Docker containers. So this will actually be a Docker container that is taken from just global Docker registry, but inside of that container is a Windows VM. So let's deploy it and see what happens. Of course, for that, we will be using idempod deploy command. So I'll just hit it this way. And again, the deployment part itself is pretty quick. For Eve to actually download that container and start a VM, that takes a lot of time. So let's actually immediately run the second one, which would be the Rancher K3s VM, again, also packaged as an Docker container. So we'll deploy that one as well. And unfortunately, we have to wait because my network is not too fast, and Windows VM is 7 GB. So we'll do a jump cut again. So enough time has passed. So how do we even know that something is up and running on Raspberry Pi? Well, we will use another subcommand of pod. This time it's ps, again, something that should be very familiar to all of the Kubernetes users. So let's just do eden pod ps. Ta-da! We have two of our VMs up and running. So as you can see, we actually have network ports proxied back to the Raspberry Pi itself from the VM. So because my laptop and my Raspberry Pi are on the same network, I can just directly connect to Windows RDP in this particular case and to Kubernetes control port. I actually already have the Kubernetes config prepared, in the interest of time. So let me just run the deploy command. Actually, let me run an apply command, with the most traditional apply there is, which is the nginx server. Okay, so that'll take a little bit of time. The deployment is created. And if we do the usual kubectl get pods, ta-da, we have our containers running inside of the K3s VM on Raspberry Pi, all with the help of Eve. All right, so with demo out of the way, there's just only one thing left, and that is invite all of you to come and check out Eve. So there's a website, go there. We have a pretty well-attended, I guess would be the way to put it, Slack channel. There is a URL to the Slack channel from the project website. Just check it out, hang out with the community and help us answer all of these interesting questions, right? Some of them are actually pretty thorny because like I pointed out, it may be the case that we need to completely collapse the K3s, the runtime, and the Eve, the operating system, into a single thing. And so far, we haven't really been able to figure out how to do it. If any of you have good ideas, that would be very much appreciated. But it's definitely something that we actively think about. We feel that building this Android of the edge, it takes a village. So hopefully all of you, or at least some of you, can join us and help us do that. With that, thank you so much, and have a good day. Bye-bye.